Hello! In this video, we are going to prove the following theorem. Let a be a non-zero real number. Then for all integers n, a to the power of n is non-zero. Now let's first remind ourselves of our definition of non-negative integer exponents. Let a be any real number. For each non-negative integer n, we define a to the power of n to be a real number, recursively as follows. A to the power of 0 is going to be equal to 1, and a to the power of n plus 1 will be equal to a to the power of n times a for every non-negative integer n. Now we also have a definition for negative integer exponents, where we define any non-zero real number to the power of a negative integer. Now the definition of that isn't going to be important for this video, but rather the following property that we have proven, which is the following. Let a be a non-zero real number. Then for all integers m and n, a to the power of m times a to the power of n is equal to a to the power of m plus n. Okay, so now let's get into proving this theorem. To start out the proof, since we're trying to prove a statement about every integer n, let's give ourselves an arbitrary integer n. From here, the whole goal is to show that a to the power of n is not equal to 0. Now, according to star, what happens if we do a to the power of n times a to the power of negative n? Well, by star, we can just add the exponents. This is just a to the power of n plus negative n, which is a to the power of 0. And according to our definition for non-negative integer exponents, a to the power of 0 is equal to 1. And 1 is not equal to 0. So what this tells us is, when we multiply a to the power of n and a to the power of negative n, the result is not 0. Therefore, a to the power of n can't be equal to 0. What goes wrong if a to the power of n is equal to 0? Well, then we're doing 0 times a to the power of negative n. Any real number times 0 gives us 0. So the product of these numbers is 0, contradicting the fact that it's not 0. So we must have a to the power of n is not 0. And that is exactly what we wanted to show. So this shows if n is any integer, then a to the power of n must not be 0. So that proves exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.